Okay, we'll get started now. So it's just after 10. So welcome everybody to the HyCoRe Hydrogen Cost Reduction End of Project webinar. So I'm Michelle Hitches. I'm from the Offshore Renewable Energy Catapult. I'm very pleased to have managed this project on behalf of NGN, who unfortunately can't be here today. So just to give you a little brief overview about what HyCoRe has been doing. So over the last year, so we've been through the discovery phase and now we've moved into the alpha phase. HyCoRe has been looking to identify UK regions with strong potential of offshore wind and how that can interject into the gas network. So we've been doing that a number of different ways, but I'm not going to spoil the rest of the team's presentations. So I'm going to pass you straight on now to Rashina from Arup.
Good morning, everyone. My name is Rashina Jagdari, and I am a senior engineer at Arup. So today I'm going to be presenting around the work we've been doing around the national modelling of offshore zone considerations in order to identify high potential zones for offshore hydrogen production. And I'm going to be focusing on the work that's been undertaken by Arup. So go on to the next, please. So the objective of this work was to identify areas for offshore wind development that supports green hydrogen production offshore. And the methodology we adopted includes the adoption of SCALE, which is a tool by Arup for a digital offshore wind deployment model in order to assess those high potential areas for offshore hydrogen development. So the stages of modeling that were undertaken are shown on the slide. So we started with collating data and agreeing project-specific inputs, including a study area and a boundary. And then we performed the baseline levelized cost of hydrogen analysis, followed by assessing the influence of geospatial constraints on those deployment locations, and finally visualizing our outputs and drawing out conclusion and outcomes for the project. Next one, please, Michelle. So in doing so, we've adopted a data-driven approach that uses SCALE to map out levelized costs of hydrogen across the study area, but also tests a range of geospatial scenarios to balance between LCOH and other marine activities that happens around the seabed. So we looked at 3 geospatial scenarios in this study and varied the treatment of those constraints. We've also incorporated in the model onshore hydrogen connection locations in order to understand their influence on the preferred locations for deployment. These locations were identified from latest industry research, as well as verified against the study undertaken by OREC on this project, which considered gas and electrical grid connectivity capacities, hydrogen storage capabilities, and other constraints. Next one, please. So the assessment was carried out in 2 steps. First, as I said, we determined the unconstrained levelized cost of hydrogen, and that is the LCOH if geospatial constraints are not considered. This assessment showed that LCOH is highest in the southwest region, which is zone 0 on the image, and another 6 broader zones, zones 1 to 6, exhibited lower LCOH, with the primary drivers being shallower water depths, milder mid-ocean conditions, higher wind speeds, proximity to construction and operation ports, and proximity to hydrogen connection locations. Next one, please. And the second step was then to investigate the effect of changing the treatment of those geospatial constraints on the location for optimal deployment across the 3 scenarios that we analyzed. So in each scenario, the geospatial constraints were either treated as hard, soft, or they were simply not considered. Areas of the seabed that overlap with the hard constraints are completely excluded from the analysis, whereas for areas that overlap with soft constraints, cells with lowest LCOH is therefore prioritized. The image on the right shows the hard constraints in the highly constrained scenario, which depicts an upper bound case where most of the constraints are treated as hard, and therefore we've got less seabed available for offshore deployment. Next slide, please. having done the LCOH and the constraints analysis, we then use a loss function to prioritize cells for deployment model in each geospatial scenarios. This is the sum of the normalized LCOH and the normalized constraints area overlap. And therefore, this gives us an idea of where best to deploy offshore wind locations. This assessment was carried out for a total of 29 number of 1 gigawatt capacity offshore wind and hydrogen projects, with a view of commercial operation dates ranging from 2032 to 2050. So this deployment model therefore identifies year on year the most optimum location for these 1 gigawatt clusters amongst the available cells by selecting the ones with the lowest loss function, and also outputs the most optimal foundation option for these clusters. Next one, please. So we've seen that varying the treatment of geospatial constraints across the 3 scenarios incrementally reduces the seabed area available for deployment, as we can see from scenario 1, which is minimally constrained, up to scenario 3, which is highly constrained. So the results of this analysis demonstrate that consideration of those factors materially affect the preferred deployment locations alongside the fundamental drivers of LCOE or LCOH, which are wind speed, water depth, metocean conditions, and distance from shore. For example, in the highly constrained scenario, we can see that there is significantly reduced area for deployment, specifically in shallower waters and close to shore. And as a result, we can see a higher proportion of these clusters, which are shown by the orange and pink dots, deployed in deeper waters, and also where jacket foundations become more preferable compared to other scenarios. Next one, please. So in summary, the zones identified through this analysis present lower LCOH alongside lower constraints with other seabed users, and therefore they represent the zones where we've got strongest opportunities for developing offshore wind and green hydrogen production projects. However, there are several other factors that would impact the decision of a single offshore site for a project like this, which should therefore be considered in more detail in future stages of development. This work has then subsequently informed the modeling of a selected regional specific solution to better understand the infrastructure solutions that provides connectivity between offshore wind production areas and energy, which was undertaken by Kinuel and Unesis. So thank you very much for listening, and I'll now pass on to Mick.
Thanks, Rashina. If you just give me a second, I'm just going to, there we are. Hopefully, can everybody see that? Not yet. Let me try again. Sorry, just give me a second.
Yeah, we can see that, Mick.
Okay, great. Sorry. I'll just pull that to full screen if I can. There we are. Okay, good morning, everybody. My name is Mick Flynn. I'm a partner and co-founder of Unesis. And the objective for Unesis on Work Pack 2 was to understand the areas of the country, both onshore and offshore, that could be strategically the next hydrogen from offshore wind zones. So this would enable greater understanding of the viability of green hydrogen. So we began by utilising our digital North Sea portal to define infrastructure that could be repurposed both onshore and offshore. And we also looked to lay out proposed new hydrogen lines, which you can see in Scotland, down in the Humber region, and now on Teesside. And then we would then model a specific region, allowing us to understand infrastructure solutions that will provide connectivity between offshore wind production and energy consumers and the gas network. So the model here is showing the gas coming in from the Everest and Lomond fields into the CATS network, the Bray gas pipework coming in. We've modelled in the existing gas networks that could be reused. The power lines are in there. It looks a little bit like a dog's dinner at the moment. There's a lot of data that's in there. But the Teesside Industrial Complex, which was the exemplar region chosen for Work Pack 2, is highly congested. There's a lot of history there, a lot of infrastructure, and it's full of complexity and risk, both in terms of cost and environmental impact. So understanding how physical assets, both old and new, integrate with one another and having the correct data was essential for us but it was essential for everybody on the path to decarbonisation. So the first thing we had to do was really to get the definition right. And this is a work in progress. We've started to get a clearer understanding of the existing infrastructure. We've got a lot of utilities in there, which you can see, which are colour-coded. And we've got a lot of process facilities in there as well. So the red is the power, the green is the hydrogen, the blue is the CO2 lines that are going out. The pink shaded areas are actually the BP hydrogen network that has been mapped out by a company called Ardent, based, excuse me, down in Leeds. And we've spoken to them on the work that we're doing, and we can also see one of the storage potential areas there, which is the Teesside anthracite caverns. So we moved on, and then for our digital twin of the region, we're using a game engine software to create an immersive, collaborative and interactive smart digital replica of the Teesside region. So the innovative use of game engines to create an immersive digital twin provides the ability to combine information with the digital replica and use it to run simulations that reduces decision-making time and enhances collaboration. It also enables those using the twin to make more informed decisions around, say, infrastructure changes or, say, asset performance. And our idea for the Teesside scene for HyCoRe was to create a digital replica of the industrial complex that would allow us to challenge it virtually and change it easily. We would be able to say, here's your asset, this is the predicted hydrogen usage, energy and carbon output. We could also use the scene for community engagement, visual impact studies, or even master planning. And there's also an underlying engine in the tool for life cycle management. So initially accessing the onshore detail for pipeline storage and emerging hydrogen businesses was an issue. However, we've spoken to many parties about HyCoRe, and we were able to leverage quite a lot of data around both the onshore and offshore as-built infrastructure and also proposed developments. And what it's helped us to do is to identify hydrogen offtakes within the region, look at congested and difficult areas of electrical grid connectivity, look for uncongested and easy areas for gas connectivity, and certainly looking at repurposing existing onshore and offshore infrastructure. Okay, I hope that was informative. Okay, handing back to you, Michelle.
Thank you. Michael?
Yep, good morning everyone. So I'm Michael Walsh. I'm a research and development engineer at ORE Catapult, situated within the hydrogen systems team, which has been working on Work Package 3. Work Package 3 is looking at some of the technical challenges around actually integrating a electrolyzer either directly with a wind turbine or looking at some of the other possible system layouts. So if you could move on to the next slide, please. So task 1 as part of the work package is looking at this top level down system layouts and the various different configurations and what technical barriers that might occur in each of the different scenarios. So the top image there is looking at the direct integration of a hydrogen production facility with a wind turbine. So this is looking at smaller scale electrolyzer or hydrogen production and the sort of electrical management that would need to be in place in order to manage a varying output wind turbine with a electrolyzer that
We're having some challenges, Michael. We'll skip on and come back to you in a minute, okay? Natalia, we hand over to you.
Yes, thank you, Michelle. Thank you very much. Good morning, everyone. I am Natalia. I'm a researcher at Newcastle University. And in the same work package that Michael was just presenting, I will now present to you our role and work. Next slide, please, Michelle. So as Michael mentioned in the beginning, the green hydrogen from offshore wind systems, their configuration is not one or unique, so that's not fixed. And there could be a lot of potential configurations out there. One of them is, for example, if you produce hydrogen offshore, you may want to transfer it to shore using a pipeline. But if you want to produce it onshore, you may want to have a cable connection from the wind turbines to shore. And this basically brings a range of changes to the system, the components of it. So the question was, when you design the systems, if an extreme event occurs, how can you know at design stage which configuration is more resilient or robust? So this is where our work that I will present now here came. Next slide, please. For this purpose, we took 3 steps that I will mention now. Next slide, please. The first one, which naturally also brought the next 2, was to define which system exactly are we talking about. So which is exactly the system, where does it finish, and so that we know which is its resilience and robustness. Next slide, please. So given that we have this, we're not sure about which is the system configuration, but the good news is we do know there is wind in and green hydrogen out. So given this, we defined that our system will finish, next slide, please, Michelle. Right there. So basically it will finish when it has supplied the hydrogen to end users. So that could be provided in storage or, for example, inserted in a pipeline, as we saw earlier, like Mick showed. And so this was important because in the beginning, for example, a natural thought could be, why are you not assessing resilience according to the hydrogen produced only? But in the case that we have a configuration where hydrogen is produced offshore, if something has happened, an extreme event that for some reason you can't use the pipeline, even though you can produce hydrogen, you cannot supply it, which is why we thought it was important to define the system boundaries. Next slide, please. The second thing was define resilience and robustness, but also to understand and answer the question, how do these two relate? What is the relevance of these two terms for the systems that we have in this project? Next slide, please. So given that, as we can see on the left, we have defined that our question is, can hydrogen be supplied to end users when an extreme event occurs? According to the International Energy Agency, actually robustness is a component of resilience. So for this work, therefore, we have defined robustness according to, can the system supply the required hydrogen despite extreme events? So how robust is your system when something has happened to it, when it has extreme pressure? And the IEA also said, though, that resilience is composed of two more things that we deemed important, which is why we added them, and I have in gray on the bottom right here. That is resourcefulness. Do you have the resources to actually maintain the required hydrogen levels? And the final one was recovery. How fast can the system recover? So in the definitions, to fully be able to describe resilience, we have proposed this analysis and definitions for the specific systems. Next slide, please. And these led us to the assessment framework and quantification metrics. So we have proposed 3 metrics that we believe are useful to describe resilience and robustness of these systems. Next slide, please. So looking at the left, given that you know your hydrogen supply rate, so how fast can you supply hydrogen? What are your system components? So which is finally the system configuration that you will have? What is the unit price? How much does hydrogen cost? And what is your available storage and other parameters? Given that an extreme internal or external event has occurred, we have proposed 3 metrics to assess and quantify resilience and robustness. Looking at the right, the first one is what we call hydrogen not supplied. And this metric describes the quantity of hydrogen that was not supplied because of the extreme event that occurred to the system. So that would be the kilos of hydrogen or the kilowatt hours of hydrogen that were not supplied. The second one was what we called a ratio of hydrogen not supplied. That's a percentage. And the reason why we wanted to add this is, in case you want to compare 2 systems that are not exactly the same at design stage, for example, and for some reason they produce different amounts of hydrogen, at least the ratio will be able to tell you this will lose 3% or this 5%, depending on what has happened, so that you can compare systems that may not compare like for like. And the third one was, what is your monetary or financial losses that go along with these? So what is your lost revenue because of the hydrogen that the system was not able to supply? Next slide, please. So to summarize, we're presenting here a figure which at the heart of it has the resilience framework. And then on the left, we can see that it's important to introduce to this framework, which is your system, which are your components, what event occurred, unit price, and other parameters. And then as outputs, we have shown on the top right, robustness, which was within the scope of this work, but we also introduced recovery and resourcefulness, which are important so that someone can fully represent and assess resilience. Thank you. I will pass on now to Anna.
Should we just see if Mike is back? Sorry, Anna. Oh, we still can't hear you, Michael. So we'll move on to Anna.
Sure, thanks everyone. Hi all, my name is Anup Nampir. I work as a research engineer at the Offshore Renewable Energy Catapult. And I'm here to present the work that we at the Catapult did around validation and demonstration infrastructure optimization within this project. Can I have the next slide, please, Michelle? So this work stems from previous work that we did within HyCoRe discovery, which was the previous phase of this project, wherein we had reviewed technology gaps and test and validation requirement gaps within the hydrogen space. And our focus in work package 4 of the HyCoRe Alpha project, that's the current project, was to explore enhancements of existing testing facilities that both ORE Catapult and Northern Gas Networks, NGN, have to fill some of these gaps we identified. And the work was broadly divided, or we had 3 tasks within this work package. One on market study, which is like an extension to work that was already done in HyCoRe discovery, then going into facility specification and then costing. And I'll speak about all the 3 tasks in a bit more detail in the following slides. Next slide, Michelle, please. The first task was the market study. And as I said, it was an extension to what we'd done within HyCoRe discovery, wherein we reviewed existing hydrogen system test facilities in the UK, EU, and US. And this image there gives you a snapshot of one of the outputs from this piece of work. This is, you can see all the test facilities listed on the left and the kind of test capabilities and test areas they work in on the top row. Next, can you click, please, Michelle? And we kind of extended that work to look inwards at our own testing capabilities, both at ORE Catapult and NGN, and came up with a similar matrix of capabilities. Click, please, Michelle. And the next part of this task was to look at what, or to gauge what the industry's perceived needs are in the hydrogen system testing space. And we followed, we did 2 things there. One was to look at all the different components that constitute a hydrogen system, right, from the production technology, the balance of plant, including the wind turbine in this case, and also look at or come up with potential test requirements for each of these components. If you can click again, Michelle, please. And this work drew a lot out of all the stakeholder engagement we at the Catapult have had over the last few years with a variety of different players, right from electrolyzer manufacturers down to project developers and power converter developers, etc. Again, this image is just a snapshot of where we are with that piece of work. And that kind of followed on nicely to the next task, which is around facility specification. And the first aspect we looked at there was what are the kind of tests in more detail that we would like to do for hydrogen systems integrated with wind turbines. And we kind of classified all the test requirements from the previous work into 3 main classes of tests. The first one is functional testing, which is basically electrolyzer testing, looking at assessing its efficiency, response times, durability, etc. So it's all system or component based, electrolyzer testing based. And then looking at integration, wind turbine electrolyzer integration. And this is more relevant to topologies where your electrolyzer doesn't have a grid connection. So it's off-grid operation, which means it's a bit more challenging to operate that isolated microgrid. And there are a lot of requirements that need to be met to operate such systems effectively. And of course, there's a lot of testing activity that we needed around that as well. And the third one that we identified was for grid connected systems. As the size of electrolyzers increase and they connected to higher voltage parts of the electricity network, they would need to comply with the grid code. And there's also the possibility of using some of the electrolysis, some of the electrolyzers as a flexible demand through which they can access the some of the ancillary service markets in the UK. So there's some testing around that as well. And you can click, Michelle, please. And based on the tests that we identified, and from all the previous work in the first task as well, and our current testing capabilities, our idea is to focus more on the two test areas that I've circled there. What's electrolyzer testing that kind of covers functional tests, and full system testing that becomes important for both integration, wind turbine electrolyzer integration tests, and potentially grid compliance as a service tests as well. Next slide, please, Michelle. Next aspect we looked at was how would we go about doing these three types of tests, and what are the enhancements we need to make to our existing capabilities to perform these tests. The image there shows you the different ways through which you can test such systems. So on the extreme right, you have field testing, wherein you have your wind turbine or your device of interest in the field operating, and as it shows on the top there, that's high confidence because you have the component in the field, but then it's expensive, and general it would take a long time to perform these tests. And on the left extreme, you have virtual testing, which is a lot of numerical modeling based testing, which is low cost, fast, but low confidence. And what we have in the middle is system testing and hybrid testing. That's what we want to focus on here. You can click once, Michelle, a couple of times actually. Perfect, thanks. So in system testing, essentially what we're having there is a full system being tested in a test facility. And with hybrid testing, it's similar, but instead of having the whole system as hardware, we're having parts of the system emulated in software and parts of it in hardware, and that's basically where our the ORE Capital strength lies, and that's what we want to pursue further here. And for hybrid testing, as the image at the bottom shows, there are 4 main components that we deal with. So we had mathematical models of certain components or subsystems. The second part is a digital simulator. So these mathematical models are run in real time in these simulators. And you have grid emulation capabilities. And what the grid emulators do is they kind of, they're the interface between the control signals from the digital simulator to the actual hardware that's on the test. And that's what you have on the right there. And in this case, the example there is of an electrolyzer being tested with its power conversion and storage as well. And if you can give me a click, please, Michelle. Yeah, so I think there's a few bits missing there on the screen, but then what I had there was, that's okay, thanks. So what I had there was, where we are with this kind of testing capability within the ORE Catapult. So we've got mathematical models of various components that we've been developing, and we've kind of used them in real-time simulators in the past, right from wind turbine powertrains, electrolyzer models, battery systems, etc. We have hardware in the loop facility capability already using a couple of real-time simulators that we have. We have grid emulation capabilities as well. So we've got an 18 MVA grid emulator, and we will soon be commissioning a 1.2 MVA emulator as well, which is more flexible than the big system that we have. And what that shows is that the missing element is the hardware and the test in this case. And our idea is, we've identified the infrastructure that goes along an electrolyzer test facility to be the enhancement that we would like to make at the facility that we have. The next slide, please, Michelle. So that brings us to the specifications of what this facility might look like. And so we started off with a list of all the components that would constitute this facility, and looked at all the different technology options that are there and ranked them according to technology maturity there. Click, please, Michelle. And just a snapshot of some of the discussions that we had and some of the decisions we made. For example, we decided we wouldn't have any high pressure storage because of the more arduous health and safety requirements there. Something on the hydrogen offtake, we decided to go down the route of fuel cells. Click, please, Michelle. And what finally came through all of that work was the this process flow diagram of this test facility. So what we have in the middle there is electrolyzer, and everything around it is what we are trying to develop as the enhancement to the test capabilities that we have. I must say that the power supply emulator side is something that we already operate. So that's something that we already have. But everything to do with water supply, drainage, how and what we do with the hydrogen that is produced, storage and offtake through the fuel cell. And the idea behind this test facility is that the electrolyzer would be the device on the test, and that would be something that clients would bring to the site to test. And we've considered, everything from the power supply requirements, the footprint of. So can you give me a click, please, Michelle? Yeah, so again, power supply requirements. We've kind of identified that the biggest electrolyzer that we potentially could test on site would be a 12 megawatt electrolyzer with a 2 megawatt fuel cell, doing some power recirculation. There are footprint constraints on site. That's at a Blythe site that we work at. And that gives you this image here gives you an indication of how much area or footprint would be required for each of the different components and how much is left for storage. That is useful as well. Can you give me a click, please, Michelle? So this a couple of images here just to give you a taste of the tool that we developed through this project. So the first tool that we have there is so basically it's a very user-friendly Excel file. You can change the power rating of the electrolyzer here, for example, and it does all the calculations that you need for water supply drainage requirements. Click again, please, Michelle. And this example is again the same tool, but looking at storage possibility, at site based on the footprint required. And at the bottom there, you can see, so for, we've done some analysis about different electrolyzer power ratings and fuel cell power ratings, and we know what the storage capability is at the site based on all the footprint analysis we did. And so, for example, having a 12 megawatt electrolyzer with a 2 megawatt fuel cell would give us about 30 hours of continuous testing that's possible before the storage gets filled, and we need to, kind of use the hydrogen then. Click again, please, Michelle. Once more, please. Yeah, so that is around the test facility specification. The next task, the third task within this work package was on the costing. So we can identify what are the infrastructure developments that need to be made to allow electrolyzers to be tested at our Blythe site. And the last task was around the costs, both operational costs, including cost of utilities, personal costs, maintenance costs, and also cost of the infrastructure, like, the 2 megawatt fuel cell that I spoke about earlier, and, all the cabling and pipelines and foundations that are required here. Next slide, please, Michelle. And this image just gives you a quick snapshot of, it is just running costs, operational costs of this proposed test facility. And I think that the key message there is a lot of it is on and around electricity charges. There's a bit in gray in the previous slide. And so that opens the question, do we actually try and run this facility with electricity that we buy from the grid, or do we do something else, have our own generation on site? That's, it's an open question. Next slide, please, Michelle. And I must say, so we don't have any concrete plans to actually develop and deploy such a facility on our site at the moment. This is just the first step or the first stab at looking at what our site can hold. So the idea was to come and get the envelope of the power rating, storage, etc., that we can have on site based on all the constraints I spoke about earlier. And of course, even though I've spoken a lot about a 12 megawatt electrolyzer test facility, we, if and when we get to the point of actually building this facility, we wouldn't be building a 12 megawatt system in the first, as the first step. It would be done in phases. We'd probably look at a 1 to 2 megawatt facility to start with. And what this facility would offer the industry. So you've got commercial testing that we can do for electrolyzer manufacturers, for example, project developers, R&D projects possibility there in the electrical wind turbine hydrogen integration space, training programs possibility, and it's a key enabler for all the offshore wind hydrogen targets that we have. Next slide, please, Michelle. That's the last slide, just quickly summarizing the key outputs from this work. So the first one that relates to the first task is on the gaps, the technology validation and demonstration requirements that we've identified through all the engagement we've had and the review we've done. The second one around facility specification is the tool or the set of tools we've developed that lets us determine specifications for all the infrastructure required for deploying such a test facility. And what using that tool showed us that is that there is potential for developing such a test facility at our Blythe site of the ORE catapult. And the third main output there related to the costing task was the tool that we developed, again, to estimate the costs associated with the infrastructure required and for running such a test facility. Thank you all for your time. Now I hand over to Chris Mullen from Kennewill Energy to take over.
Hi, I'm not sure if we're getting Michael back or not. Do you know, Michelle?
We'll give them a try when we get there.
Okay. Hi, my name is Chris Mullen from Kennewill Energy. I'm a senior engineer. So work package 5 was around routes to market, and there were 3 subtasks. One subtask was done by Arup, and that was on markets and regulation. I'm going to present very briefly on their work. Then I'll move on to the work that we did at Kennewill Energy on hydrogen storage. And we may or may not have a presentation on the offshore renewable energy catapults work on supply chain maturity analysis. So next slide, please, Hannah. Sorry, Michelle. So yeah, very briefly on the work that Arup did. They summarized the existing regulatory framework associated with hydrogen production from offshore wind. They identified gaps and barriers, and they developed actions to address the regulatory gaps, specifically for hydrogen. Next slide, please. So brief summary of the conclusions from Arup. The regulatory framework is complex. There don't appear to be any absolute barriers to the development of electrolyzers powered by offshore wind. However, there are areas that will need to be updated to cater for the development of the hydrogen industry in general. So that's a very brief overview of Arup's work. We'll now move on to our work at Kennewill. So we were looking at the hydrogen storage requirement, and we did this by generating 1,000 sets of statistically representative time series for generation and demand. Generation was based on a 1.5 gigawatt wind farm and using 40 hours of hourly wind speed data. The demand data was taken from various local distribution zones from Northern Gas Network, using or assuming 20% and 5% hydrogen blended with natural gas. Next slide, please, Michelle. So just to kind of illustrate curtailment, we've got a fictional graph of demand in brown and generation in blue. You can see in the middle of the graph, we've got power versus time. In the middle of the graph, generation is exceeding demand. So without storage, this demand would be curtailed. If we were able to store this generation instead of curtailing it, we could feed it back to the demand just a little bit later on when the generation dips below the demand. So in the models, we calculated the energy curtailment over the year using the the time series generation demand models, and a storage model that we developed. Next slide, please. So this is the kind of what the results look like. There's quite a few things going on in this graph. On the y-axis, we have the annual energy curtailed in gigawatt hours per year. And then on the x-axis, we're changing the size of the storage. So the very lowest curve, this light blue curve, is the mean annual curtailment over those 1,000 simulations for each scenario. The upper curve, the black dashed line, is the maximum annual curtailment, so the simulation with the maximum curtailment. And then this blue line in the middle is the 95th percentile. So what that means is that 95% of the simulations had a curtailment at or below this value. And then what we've done is we've taken this 95th percentile line and found the point where zero curtailment occurs, and we've indicated that with this red dotted line to give a storage size for that particular scenario. So this result is one of 7 different scenarios. Next slide, please, Michelle. So here I've got a table of results. The second column is the local distribution zone that we used. Then we've got hydrogen blend. We've calculated the ratio of generation to demand. So in general, you would expect there to be, you might perhaps expect there to be more curtailment when the generation is large relative to the demand. And then the storage result we had for the 95th percentile in the final column. There's not an obvious relationship between the generation to demand ratio and the storage required. It really is very dependent on the time profiles of the generation considered against the time profile of demand. Just to note, the last scenario, we added in a model of wind farm maintenance that reduces the demand, the energy generation over the year, and that means that the storage required is a lot less. And you can, comparing with the scenario without maintenance, which is the one above, number 6, you can see that it makes a very significant difference. Next slide, please, Michelle. So the key takeaways, curtailment is very dependent on the demand and generation size, which is kind of obvious. If the annual demand is very low, in general, the curtailment would be very high. If the annual demand is very large in comparison to the generation, there would be low or perhaps even zero curtailment. The big point is, however, that curtailment also depends very much on the time variant profiles. There's not a scalable way to calculate that we found. And the final takeaway is that offshore wind maintenance has a very big impact, and that is because, as I said, it changes the generation, the annual generation energy relative to the annual energy demand. So that, I think, is my final slide, Michelle. I don't know if we've got Michael or not.
Are you there, Michael? No? Okay, Chris, you can't hear Michael. Do you want to talk through these slides or do you want to leave it?
Yeah, I don't really feel that I can do this work justice, unfortunately.
No
So
problem.
hand back to you, Michelle. Thank you. Oh, sorry, just to address there's a question in the chat about regulatory barriers. I'm afraid I can't really answer that question either. That was work done by Arup, but I believe there's a public report coming at some point where you'll be able to look at that.
Great, thanks, Chris. And thanks everybody for listening. Sorry about the technical hits with Michael and not being able to do the ORIC work. What will happen after today is we will send the slides out and also the recording. But my contact details are on the screen. And if you've got any questions that you'd like us to follow up on, we can do that after the event. So thank you very much for listening today and have a great day. Thank you.